All right. So welcome back to another Math 230 231 GSG session. So for this week's GSG session, we'll be covering chapters 14.5 and 14.6. So I'll start off with a bit of a rundown of what we'll be covering. So for 14.5, it's basically the chain rule. So for this, there isn't much to say about 14.5 other than drawing out tree diagrams. And we'll be going over a lot of examples from the textbook for 14.5. Yeah. All right, and then we'll also be covering 14.6, which is the gradient vector or gradient vectors and directional derivatives. Yeah. So for 14.6, a few key points I'll be discussing we'll be seeing in this examples will be what a gradient vector is. So you guys should probably be familiar with this from lecture. So given a function, f with the variables x, y, z, the gradient vector of f would be f of x, y, and f of z, which is just the partial derivative in each respective component, right? That's one thing to note from 14.6. I'll be splitting the examples to the three different parts. So I'll start with gradient vectors. And then another thing to note from this chapter is directional derivatives. Yep. So if we're given so let me just write it down first. So normally you'll probably be seeing directional derivative in this form, where you have a function f and you have a unit vector u. And we're trying to find the directional vector of f along u. So we'll be covering examples dealing with the directional vectors. And then let's see, what else do we have? So I'll clump this up as part A for 14.6. And then we have maximum rates of change. That was also covered in 14.6, which is essentially the magnitude of your gradient vector. If, let's say, the function f has variables x, y, z, and then the direction of these gradient vectors. And lastly, so this is going to be part B. And then the last thing we'll be covering from 14.6 is this whole idea of tangent planes to level surfaces. And we'll be using a couple of equations for that, as we'll be seeing throughout the examples. All right, so any questions regarding the lesson plan for today? All right, perfect. All right, so let's get started with 14.5. Let's start off with an example. So I have, let's see, start off with number 1 in 14.5. So for number 1, it states that you have z is equal to xy cubed minus x squared y. And you have x is equal to t squared plus 1, while you have y is equal to t squared minus 1. So when I initially started off doing these chain rule questions, what I did was I used a tree diagram to better visualize what I'm trying to take, which derivatives, basically partial derivatives, I need to take. So I start off with my bigger function of z, my outer function basically of z, and then z has variables x and y, is dependent on the variables x and y, while x and y have variables t for its respective equations. All right. And then from that, the question is asking to find what dz of dt is and what dw of the or. All right, so in this case, it'll be what dz over dt is. Okay. All right, so let's look at this question. So for dz over dt, just looking at the tree diagram, we can see that in order to get to t, there are two different routes. There is the route of going through z, x, and t, and that's the route going from z, y, and t. Right. In this case, it's pretty straightforward, as you see that each variable is represented with t, but with like other questions we'll see later on, sometimes equations are dependent on more variables, more than one variable, right? So in this case, we can see that dz over dt is essentially dz over dx times dx over dt, right? And usually I represent that by saying that each line from the tree diagram is that right there. And this should be familiar from lecture. So this is dz over dy and dy over dt, right? So if I were to go from z to t using this x path, I basically just multiply dz over dx multiplied by dx over dt, and that will give me dc over dt since the x's cancel out, right? Shown here. All right, so that's one way, and another way of going through to t is dz over dy times dy over dt. Okay. Yeah, this should be 0. And so if we actually solve for dz over dt, we have dz over dx, which is the partial derivative of z in terms of x. So that's gonna be y cubed minus 2xy for dz over dx. Then dx over dt is going to be 2t. Right? And then we're adding that with dz over dy, which is gonna be 3y squared times x. Yes, and then minus x squared, since we're treating the y's as the variables. And that's going to be multiplied by the same equation, right? And so if I were to simplify that down, I would get, so let's see if I can expand that out. So we have y, so 2y cubed t minus 4. Actually, let me just group up the two t's. Probably be a lot easier. So what I can do is I can factor the 2t from this whole expression, and I can just write it out as this. There we go. And so dz over dt is going to be this, right? So the big thing about chain rule, or rather how I approach chain rule questions, is just using this tree diagram right over here. All right, let's look at another question. Let's look at one with more variables. So let's look at number 8 from 14.5. So number 8, okay. So for number 8, we have z is equal to x minus y to the power of 5. And then we have x is equal to s squared t, and then y is equal to st squared. All right. So again, I'll start off by drawing out the tree diagram. So it'll be z is dependent on x and y, and then x is dependent on s and t, while y is also dependent on s and t. For this question, we're trying to find what dz over ds is and what dz over dt is. Yes, since t is the other variable. And you see for this case, like compared to the previous question, we have more variables where, like in the bottom of this tree, like in the first question, everything was just dependent on t. Well, in this question, we see that equations x and y are actually dependent on both s and t. So yeah, something to note. All right, so let's start off with dz over ds. So just using this tree diagram, that's going to be path 1 and path 2. So it'll be dz over dx times dx over ds plus dz over dy times dy over ds. Okay, so that's going to be my formula to find what dz over dx is. Okay. Now let's actually compute this out. So dz over dx is going to be 5 times x minus y to the power of 4 multiplied by dx over ds. It's going to be 2st, right? Yeah, plus dz over dy, which is going to be the same thing, but be a negative 5 instead because of the negative y inside. So it's going to be 4, and then we're also doing dy over ds, so that'll be t squared. All right, so yeah, that's basically it. You can try and simplify this down. I can take a 5 out first. So I have x minus y power 4. I have 2st plus or minus, so I can simplify this down, minus 5t squared and x minus y power 4. You can factor x minus 4 out, so x minus y to the power 4 out, and I get 2st minus 5t squared. Okay, so that's dz over ds. And then you would do the same approach for dz over dt. All right, just looking at the tree diagram, we can go through the x root, or dz over dx times dx over dt to get dz over dt. And you can also get, dz over dy times dy over dt. Okay. So if we actually compute that out, we get that dz over dx and dz over dy are what we got from the previous question for dz over ds, same exact thing. So 5x minus y to the power 4, but dx over dt is going to be s squared. That's going to be added to dz over dy, which is negative 5 x minus y to the power 4, and dy over dt is going to be 2st. Okay. Yeah. All right. And yeah, again, you can simplify this even further. Okay. All right. And yeah, that pretty much covers the basics of chain rule. So let's go over another question I have prepared. So let's look at let's look at 22, 24, 26. So yeah, let's look at 22 from 14.5. 22. All right, so in 22, we're given that t is equal to v all over 2u plus v. Right, and then u is equal to pq times the square root of r, and v is equal to p times square root of qr. Yeah. Again, the tree diagram isn't necessary. Like once you get familiar, I guess it would be easier to just get through with the solution. But yeah, I'll stick with the tree diagram for this question. So t is dependent on u and v. It just makes things a lot clearer once you write down the expressions for the partial derivatives, at least for me. All right, so we have this tree diagram, right? And we're trying to find what dt over dp is, what dt, or capital T, over dq is, and finally, dt over dr. Right, so again, the same approach with how we dealt with chain rule in the previous questions. Let's start off with dt over dp. Again, from this, you can see that there's one root which goes through u, and there's one other root. So I can, okay, something's, all right, let's see, there you go. All right. Yeah, you have to look at all possible combinations to p. Okay, in this case, there's two different roots. So in this case, you'll get dt over du times du over dp. And that's going to be added to dt over dv times dv over dp. All right. So yeah, that's the general equation for finding what dt over dp is, or the formula to find dt over dq. That's going to be the same thing as t of u times u of q plus t of v times v of q. Okay. That's just another way of just writing the same exact thing. Actually, just another way of writing down partial derivatives, right, using the subscript notation. And then lastly, we're trying to find t of r. And that's the same thing as t of u times u of r plus t of v times v of r. Okay, so I won't go and I won't actually solve this out, but you would use this again, you would use the same approach solving chain rule questions. So this is just another type of question where you have 3 variables instead of 2 variables. Okay. All right, let's see if there are any other different questions. Okay. 15. Yeah, 15 is slightly different. All right. So in 15, it says that suppose f, so it states that f is a differentiable function of x and y, and we have that g of r comma s is equal to f of 2r minus s comma s squared minus 4r. Okay. And then it gives us this table. So to draw it out, so it gives us the point 0, 0, and it gives us the point 1, 2. Okay. And it gives us 4 different options. So we have f, we have g, we have f, x, and f sub y. So that would be 3, 6, 4, 8, and we have 6, 3, and 2, 5. And the question is asking to find what gu of 0, 0 is, and what gv of 0, 0 is. Okay. So again, this kind of ties into the idea of, again, chain rule. So let's see. Yeah. So what we can see is that we have this function of 2r minus s comma s squared minus 4r. So I can say this, what I can say is that x in this case is equal to 2r minus s. Right, or am I using the right values? Oh, sorry, that was number 16. So this function, yeah, I knew something was off because we're doing R's and S's. So f is actually e to the power of u plus sine v, while it's also e to the power of u plus cos v. So yeah, actually, let me just focus on this f function, this function of f right here. This can be rewritten as f of x of u comma v and y of u comma v. And that's why over here, I'm gonna set, if we can erase this, x as equal to e to the power of u plus sine of v, while y is equal to e to the power of u plus cosine of v, right? It's in the end, we want to find a function of g, sorry, let me just erase this. It's not R and S, it's actually u comma v, right? Right. Yeah, because in the end, we're trying, this is what the question is telling us to find, right? What GU00 is and what GV of 00 is. What I can do is I can rewrite this function as x and as y. And then what I can do is, since we have that, I'm just basically gonna draw out the function. So I have, sorry, again, I'm gonna draw out the tree diagram for this question. So we have g as an outer function, while g is dependent on x and on y, while x and y are both dependent on u and v, right? So this is just another question where you're dealing with the chain rule. So if you look at this function right here, I'm just gonna take, yeah, g of u. I'll start off with g of u, right? G of u is essentially the same thing as g of x times x sub u plus g of y times y sub u, right? In this question right here, they actually give us what the g values and the f values and the fx values and the fy values. So what I can see is that g of x is going to be, yeah, sorry. Yeah, I'm just gonna rewrite this in partial fraction. And I should just leave this out. Okay, so let's see what we have. So we have x of u, that is, so we have x, right? So what we can do is we can actually find what dx over du is. In this case, dx over du is the same thing as e to the power of u, because sine v is treated as a constant, while dy over du is going to be actually the same exact thing, right? So this is going to go back to this, while this is going to go back to this right here. Okay. All right. So I'm going to rewrite this g sub x as f sub x of x 0, 0, right? And y 0, 0. That's going to be multiplied by e to the power of u plus g of y, which is f of y at x 0, 0, comma y 0, 0 times e to the power of u. Actually, to be more correct, this should actually be 0. I'll explain in a minute why that is. All right. And I'm trying to find what g of u 0, 0 is. Right. In this case, as we see right here, we're trying to find what g of u is. And from g of u, we get g sub x, right? Which is essentially f So we're trying to find what f sub x is. And then since we're plugging in u and v of values of 0 and 0 for u and v respectively, what I did was I set x, or the function x, which is right here, and I just rewrote it down as that. I wrote it down as a function of u and v. Okay. And that's why this g of x can be rewritten as f sub x of x 0, 0, comma y 0, 0, right? And you know that x sub u and y sub u are just e to the power of u. All right, so let's continue this question in the next slide. So again, we have g of u 0, 0, which is equal to f sub x of x 0, 0, comma y 0, 0. And then that's going to be multiplied by e to the power of 0 plus f sub y, right? Since we have g of y, not g of x right here. F sub y of x 0, 0, comma y 0, 0. And that's also multiplied by e to the power of 0. All right, so let's see. First, let's figure out what x 0, 0 is equal to. So if we plug in 0 into x, right? So I'm just gonna write it down right here. So if we plug in x 0, 0, we get e to the power of 0 plus sine 0. So we get this function right here. And that's equal to 1. Plug in y 0, 0. We should get e to the power of 0 plus cosine of 0. Yes, cosine of 0. All right, 2. All right, so we basically get the point 1, comma 2 off of that. That's multiplied by 1. Just going to simplify e to the power of 0 as 1. And then we have the same exact thing for f sub y, which is 1, comma 2. And multiply by 1. All right, so we're left with that. And let's see, okay. So since we don't know what the function f is, right? We have to actually base it off this table right here. And that's why they, yes, that makes sense. That's why they give us this point 1, comma 2. We do have fy, fx and fy of 1, comma 2. And they do give us the values for that. Fx at 1, comma 2, or at values u is equal to 1 and v is equal to 2, gives us a value of 2, while the fy or f sub y yields a value of 5 at point 1, comma 2. So we can say that at this point right here, and based off this table, that's going to equal to 2 multiplied by 1 plus f sub y 1, comma 2, which is 5 times 1. And that's going to equal to, what is that going to equal? 2 times 1 plus 5 times 1, which is 7. Okay. And that's going to be the value for GU of 0, 0. Okay. So GU 0, 0, and let's do GV 0, 0 now. So again, same idea, GV 0, 0. Yeah, so since we're trying to find the v instead of the u, we're essentially going to use the same equation that except for the x sub u and the y sub u. So I'm just going to rewrite that. I'm just going to rewrite this. We're still going to use the chain rule. This is just based off the idea of from the tree diagram. I'm still going to use f sub x and f sub y. Now the only difference for so many. Okay, the only difference is that max getting extra parentheses. The only difference between g of u and g sub v is that instead of x sub u and y sub u, we're instead we're multiplying this by x sub v and multiplying this by y sub v. And that is again based off this tree diagram, right? Since we use these two paths to find what g sub v is equal to. All right, so let's actually compute that. Okay. So again, I'm going to use the same value. So that's going to be, this is going to be the same thing as that, as this right here. So that's going to be 2 multiplied by dx over dv. I'll compute that later. And that's going to be 5 multiplied by dy over dv. All right, so let's see what x was. So x, dx over dv, based off these two equations are going to be, so dx over dv is equal to cosine of v, while dy over dv is going to equal negative sine of v. Okay, so just write that down. All right, so we have 2 times cosine of v plus 5 times, is that right? Yeah, dx over dv is cosine of v times 5 times negative sine of v. All right, so plugging in the point 0, 0, we basically plug in 0 for v, so that's going to be 2 times 1 plus 5 times 0. So gv of at the point 0, 0 is going to yield a 2, while gu of 0, 0 is going to yield a 7. Okay. All right, so that's number 15. Okay, is there anything else I wanted to cover? Okay. One last thing before we end 14.5. Let's cover this idea of implicit differentiation. So let's say, I'll go off example 31. So let's say we have the equation x squared plus 2y squared plus 3z squared, which is equal to 1. And the question is to try and find what dz over dx is equal to, and finding what dz over dy is equal to. Okay. Based off lecture, you guys should have covered this idea of implicit differentiation in the Calc 3 term. So it's an easy approach where if you have dz, or if you're trying to find the partial derivative of z in terms of x, and where z is a function that is dependent on x and y, we can actually draw this diagram right here, x, y, z. Assuming that f is dependent on the variables x, y, z. All right, yeah, right there. Okay. So what we can do is we can set dz over dx equal to negative f sub x over f sub z. Right. And we can also set that dz over dx or dy is equal to negative fx over fy. Okay. And you can prove this using this tree diagram right here, right? If I were to find what dz over dx is, that's essentially df over dx times or plus dz over df over dz, sorry. Right, df over dz times dz over dx, right, which is equal to some constant, let's say 0. Now, if we simplify out for dz over dx, we're going to yield this function right here. Okay. And then just prove that. So dz over dx is going to be the same thing as negative f sub x all over f sub z. And that checks it off. Okay. And again, this works because z is dependent on x and y. And you could do the same exact thing with dy over dx. Okay. So this is another way, a new way of solving implicit differentiation. Okay. And a much simpler way, a much faster way, sorry. All right, so let's actually solve this. We should already solve this. Okay, let me erase. Okay. So just using this formula right here, we have that dz over dx is equal to negative of f sub x is going to be 2x for this, and f sub z is going to be 6z. So that's going to be negative x over 3z, right? And again, f of f x comma y comma z has to be equal to 0. That's one key thing to note, right? In this case, it didn't matter because this was a constant, but if you have to move everything over to one side, okay, for big F. And then, so yeah, all right, so finding dz over dy, that's the same thing as negative f of, what is this? Negative f of y, yeah, 4y all over 6z, yeah, 6z will be negative 2/3 y over z. All right, that's basically it for implicit differentiation. So let's do one more before we move on to the next chapter. Okay, so let's look at number 34. Same exact thing we're trying to find, what dz over dx is and what dz over dy is. So of yz plus x ln y is equal to z squared. So in this case, your fx comma y comma z is going to be equal to yz plus x ln y minus z squared, which is equal to 0. Again, move everything over to one side. Okay? So let's try to find dz over dx, which is negative f sub x over f sub z. And f sub x is going to equal ln y. Yeah, because these two are going to be constants. So it'll be negative ln of y all over y minus 2z, right? Because the middle term is going to be a constant for f of z. Yeah, so that's it. Yeah, you can't, I don't think you can simplify that down. And then dz over dy is going to be negative f sub y all over f sub z, which is the same thing as negative z plus x over y. Yep. That looks like that's it. Yeah, x over y. And f sub z is going to be, again, y minus 2z. There you go. You can probably simplify this down, but yeah, I'm just going to leave it like this for now. So yeah, that basically covers everything from 14.5. All right, so let's move on to 14.6. Okay, gradient vectors, yes, 14.6. All right, so what questions do I have ready? So let's look at the textbook. All right, let's start off with number 7. Start off with number 7. Okay, for number 7, we're given fx comma y is equal to x divided by y. We have the point 2 comma 1, and we have this vector u, which is equal to 3 over 5i plus 4 over 5j in ijk form. And then a, you're trying to find what the gradient of f is. B, you're trying to find or evaluate at points or evaluate a gradient at point. And then part C, it tells us to find the rate of change of f at P in the direction of u. Okay. The vector u. Okay. So I'm going to start off with A. So again, the gradient vector is essentially, so in this case, we have two variables. So x comma y, that's going to be the same thing as the vector f sub x comma f sub y, right? So we're just taking this partial derivative of this in respect to x and partial derivative of this in respect to y. So for the x component, that's going to be the same thing as 1 over y, while f sub y is going to be negative x over y squared. There you go. So that's part A. finding the gradient of f, or the gradient vector of f. Remember, this is a vector. Okay. And then this is part A. So that's part A. Now for part B, evaluate at point. So we're given this point right here, 2, 1. So the gradient vector at 2, 1 is essentially 1/1, negative 2 over 1 squared. And that's going to be the same thing as 1, negative 2. All right, so that's part B. So A and B are pretty straightforward. Now let's look at part C now. Part C, so I'm going to recall the equation of the directional derivative, which is essentially just this. Du of f, which is equal to the dot product between the gradient vector and the unit vector. Remember, u has to be a unit vector. So we're trying to find the rate of change of p in the direction of vector u, right? So for this, so let me just check. Yeah, so we just use, basically, this is essentially just using the directional derivative formula. So we do already have the gradient vector f, and that is equal to, so at the point, so in this case, it's going to be d of u at f, which is equal to the gradient vector at point, what is that, point 2, 1, dotted with the u vector, because it's in the direction of this vector right there. Okay. So that's gonna be the vector 1, negative 2, dotted with that vector right here. So I'm just gonna write it down in vector notation. So 3/5, 4/5. Okay. Now, one thing before I go on is that, again, I want to emphasize that this u vector right here, this u vector, so I'm just gonna write it in red. Yeah, this u vector right here has to be a unit vector. Okay. So in this case, yes, it does look like a unit vector, because if you take the magnitude of that, 3/5 squared plus 4/5 squared, that, yeah, that does add up to 25 over 25. So in this case, yes, the given vector is a unit vector. So we can just take the dot product. But if you were given a vector, which is not a unit vector, you have to normalize the vector and make it a unit vector, just like we covered in early on in chapter 12. Yeah. So again, so actually solve this out, we get, again, remember, a dot product yields a scalar quantity. So in this case, we get 3/5 plus a negative 2 multiplied by 4/5. The same thing as 3/5 minus 8/5, which is -1. And that is the rate of change of f at p. Okay. So that's it, the directional derivative. Okay. So let's do another question. Number 7. Let's do number 14. Yes, we have 15 minutes. Yeah, 14. Okay. So for number 14, it's essentially the same question. Yeah, and it's just telling us to find the directional derivative. Yep. So for number 14, we're given a function g of u comma v, which is equal to u squared e to the power negative v at the point 3, 0. So p is at 3, 0. And you have the vector, which is equal to 3i plus 4j. Okay. And yeah, this is not gonna be a unit vector, so we have to normalize this later on. All right, so let's see. So first of all, what I need is, in order to find directional vector, is I need the gradient vector of g, not f, of g at point 3, 0. Yeah. So let me start off with u comma v. So u v. So that's gonna be the vector g sub u, which is gonna be 2u e to the power negative v, comma u squared minus e to the negative v. Or multiplied by negative e to the power negative v. All right, so we have that vector, and then at the point 3, 0, when u is equal to 3, v is equal to 0, we have 2 times 3, so that's 6, comma 3 squared, which is 9, and negative e to the power 0, negative 1, so negative 9. Okay. Yep. Okay, negative. There we go. Okay, so we have the gradient vector g. Now the only thing we need to do, or we need to actually normalize this first, because we're trying to find what the directional vector of g is on v. So we're trying to figure out what this is, right? So we're taking the dot product of 6, negative 9, and the normal vector of this. So let's see. So we just need to divide, so it'll be 1 over the square root of 3 squared plus 4 squared, which is 5, multiplied by 3, 4. So that's going to be 6, negative 9, dotted with, let's see, 9, 16, 25, yep. So 3 over 5, 4 over 5. Yeah. So we get 18 over 5 minus 36 over 5. Which is negative 18 over 5. Okay. Yep. And that is it for directional derivatives. Let's see. So yeah. Okay. Okay. So that's it for directional derivatives. So essentially what you need, first thing you need is your gradient vector. Evaluate the gradient vector at the point, and lastly, actually solving for the directional vector using the dot product. And remember, the vector that you're trying to compare it with, or in the direction of a vector, has to be a unit vector. Okay. All right, so let's move on to maximum rate of change. Okay, so maximum rate of change is just something to add on from the directional derivative. It's essentially just, gradient vector. So the maximum rate of change is just the magnitude of your gradient. So let's look at an example. So let's look at number 22. Yes, 22. So in 22, they give us a function in terms of s and t, which is this, and then 0, 2. The question tells us to find the maximum rate of change of f at the given point and the direction in which it occurs. Okay. So first, whenever you're trying to deal with these questions, is you need to find the gradient vector. And finding the gradient vector, you get f sub s, which is t is left as is, multiplied by e to the st multiplied by t, right? Because s is the variable for f sub s. Now for f sub t, it'll be a product rule. So it'll be e to the st plus t, right? Yeah, t e to the st multiplied by s. Get this vector right there. And then what you want to do next is evaluate it at that point, 0, 2, which is equal to the, what is that equal to? So that's going to be 0 for, oh no, sorry. So s is equal to 0 and t is equal to 2. So it'll be 4 times 1 for s. And then for t, or f sub t, it'll be e to the power of 0, which is 1, plus t is 2, or this is going to be 0. All right, so that's going to yield a vector of 4, 1. All right, and then, so that's the gradient vector. Now, in order to find the maximum rate of change of f, we just take the magnitude of f0, 2. And that's going to be equal to 16 plus 1. So it's going to be square root of 17. And that's for number 22. Now, the direction of the vector is essentially just this right here. Sometimes they write this down in unit vector form. So the direction of this could be in the form of 1 over square root 17 multiplied by the vector 4, 1. But essentially, 1 over 17 or 4, 1 is going to point to the same exact, like the vector is going to point to the same exact location, right? Since they're both scalar quantities of each other. Okay, scalar multiples of each other. Okay, so that's number 22. All right, and I think I'll end off with, yes, tangent planes to level surfaces. So let's see. 41. Okay, so let's go with number 42. Okay, this is the last thing I'll cover for today's GSG session. So for 42, we're given x is equal to y squared plus z squared plus 1. Okay, why is it not working? There you go. Z squared plus 1. And you try, and they give you this point 3, negative 3, 1, and negative 1. Okay, I'm sorry, something wrong with the whiteboard. All right, so the first thing to ask for is to find the tangent plane. Find equation of the tangent plane. And the second thing to ask for is to find the normal line to the given surface at the specified point. So normal line at point. Yep. All right, so let's start off with tangent plane. So I'm going to recall the equation covered in class. So for tangent planes to level surfaces, you were given this equation right here. So I'm just going to write it down first. Rho plus f sub y, x naught, y naught, z naught, y minus y naught, plus f sub z, x naught, y naught, z naught, at z minus z naught, right? Which is equal to 0. Yes, that should be, yep. I got no room, so that's equal to 0. All right, so solving this equation right here, what you can see is that we need a function f, right? F in terms of x, y, z. So, and that function is right here. So fx, y, z is essentially just x minus y squared plus this, or minus z squared minus 1, which is equal to 0. And now taking the partial derivative in terms of x, we get f sub x as, what is that? As 1. Yep. 1 multiplied by x minus x naught. Okay, I'll explain the x naught, y naught, and z naught in a bit. Then finding f sub y, that's going to be negative 2y. And then lastly, we get f sub z as negative, or sub z as negative 2z. Z minus z naught, which is equal to 0. Now, x naught, y naught, and z naught is essentially just the point that you're given. So in this case, we're given 3, 1, negative 1. So it'll be the same thing as x minus 3 minus 2y times y minus 1 or this is going to be y naught, this is going to be z naught. Right, so it'll be 2 times multiplied by 1, y minus 1. Then lastly, negative 2 multiplied by negative 1 times z minus negative 1 equals to 0. Right. And so the equation for the plane is going to look something like this. And clearly you can simplify this out. So you can have one constant, or yeah, combine all the constants together. Okay. So I'm going to leave it like that for now. All right, so that's the tangent plane. And then the next thing to ask is the normal line at the point. So one thing to note is that the gradient vector of f, so if I were to write it down as 1, comma, negative 2y, comma, negative 2z, yes, negative 2z, that's actually gonna point in the, yeah, that normal line. Yeah, since we're trying to find a normal line, this right here, we know is perpendicular to the surface as mentioned before. So gradient vectors are always perpendicular to the surface you're given. And so this is gonna point to the same direction as your normal line. So what we can do is, going back to definitions of lines, we can write this equation for lines where you have x minus x naught all over f sub x, which is equal to y minus y naught. Yep. F sub y, which is equal to z minus z naught over f sub c, right? Yeah, this is just another representation of lines. And in this case, it'll be the normal line. Due to the fact that the gradient vector is going to point in the same direction. So for this case, we get x minus, so x naught is going to be the same thing as 3, divided by f sub x at the specified point, which is going to be just 1. And then it'll be y minus y naught, which is 1, all over f sub y at the specified point. So it'll be negative 2. And then lastly, it'll be z minus z naught. So z plus 1 and f sub z at the specified point. So it'll be positive 2. And that would actually be your normal line. All right, let me just double check. One minutes 42. Yep, this checks off. And that is it for this question for number 42, for tangent planes of level surfaces and the normal line at a specified point. Okay. Yeah, so before we end the session, any questions regarding what we covered today? All right, perfect. Thanks for tuning in, and I'll see you next week.